The purpose of what we're looking at here is to look at factor remainder theorem. So our learning goal, we want to understand the remainder and the factor theorem, and we want to use these two theorems to help us factorize polynomials. Okay, so that's the whole point of it. We want to learn them and then utilize them. All right. Before we jump into factor remainder theorem with polynomials, I just want to draw it back a little bit and look at numbers. So if we took the number 4 and we divided it by 10, we'd say we've got the number 2 with a remainder of 2. We could take the number 3 and plug it into number 36. We'd get 12 with a remainder of 0. And the reason that they are factors solely relies on the fact that there is or isn't remainders. And so we'd say that the dividend is a factor of the number if we get no remainders. And we can see that here. 4 isn't a factor of 10, but 3 is a factor of 36 simply because there's no remainders. We can generalize this to polynomials, which leads us into the remainder theorem. So if we said we've got a polynomial p of x, and x minus a number, a, is the dividend, we can just use this terminology here. So we've got the divisor, which is, we've got the dividend, which is x minus a. We put it into, instead of being the number, we put it into the polynomial, p of x. We'll get a quotient plus a remainder. Right, now similarly, if we go back, I'll do this in a green, right? If we take the quotient and we multiply it by the dividend, we have a look at the remainder, add it, you get the original number, okay? Because the quotient multiplied by the dividend plus the remainder equals the number you had originally. So if we apply this here to polynomials, we'd say the number, or the polynomial, is equal to the dividend multiplied by the quotient plus the remainder. And if we put in that point a here, we have a minus a. So we are evaluating the polynomial at a, where x minus a is the dividend. We would see that a minus a would be 0, so it's 0 times by the quotient plus the remainder. So then p of a is the remainder. Okay, and that is the remainder theorem. If you take x minus a being the dividend and you evaluate that polynomial at that point a, that gives you the remainder. Okay, and this ties in pretty tightly with the factor theorem. Very similarly, if we say that p of a is equal to 0, then x minus a is a factor of p of x, which, if you look at the remainder theorem, makes perfect sense. You evaluate it and you don't get a remainder. That means that the dividend is a factor. And again, we can look back up here. If we take the divisor, we plug it in here, we get a quotient of 12 with no remainders, then we say that that dividend is a factor. So x minus a being the dividend, we evaluate it at the point a, we get 0. Okay, we can just take a light example here, just so we can see how this works. So we've got a polynomial p of x, it's equal to x squared minus 5x plus 4. And we can factorize this to be x minus 4, x minus 1, where these two are factors. They're factors of p of x. And if you look specifically, x equals 4 and x equals 1, right? They are our A values that are going to work here for us. So if we evaluate P of A, all right, where A is equal to 4, we say that P of 4 is equal to 4 squared minus 5 times 4 plus 4, which is equal to 16 minus 20 plus 4, which is equal to 0. As we would expect, because if we look at this point here, this is the graph y equals x squared minus 5x plus 4, and we take a look at the point x equals 4, that is a root of the quadratic. Similar with x equals 1, it is a root of the quadratic. So when you evaluate the quadratic, you get the zeros, right? So these things here are the direct factors, right? There's find two factors of P of x, okay? Now, when I've got a polynomial and I want to find the factors, I need to guess values for A, because using the factor theorem, okay, P of A needs to be equal to 0, meaning that x minus A would be a factor, right? The way I do that is I need to guess values of A, but I don't just throw in random numbers, I throw in factors of the constant term. So I'm going to try A equals 2, I might try A equals -3, okay, these are just guesses, but 2 and -3 are factors of -6, and I'll see how those two work. I might even try A equals -1, okay, they're just guesses, right? So I evaluate them, one here, P of 2 is equal to is exactly what I wanted. So I can make a little statement here. Therefore, okay, x minus 2, because A was 2. So x minus 2 is a factor of P of x. Great, so that's one factor. I'm going to look for another one. So, all right, I said I was going to try P of -3. Okay, there you go. So the two values that I guessed, they were just guesses, okay? There you go, I got them both first go, which is very nice, right? So that means that, well, I need to make a little statement here. Therefore, x plus 3 is is a factor of P of x, because this one was A equals 2, and I know that x minus, the factor form is x minus A. Here, A was equal to -3. So when you substitute A equals -3, it's a double negative, so it turns into a positive, right? So we can't get tricked up on those negatives. So that's finding factors of polynomials. Second part here is calculate the remainder for P equals -2. Okay, so I know P of x is equal to x cubed plus 2x squared minus 5x minus 6. To find the remainder, I just evaluate it, okay? Because really with the first one, I was evaluating for given points, and I wanted the remainder to be 0, because that meant I had a factor, right? Here, I'm going to get a factor, as the question is suggesting. So again, not to get stumped on negatives, just evaluating this here. That's going to be 8, -8, plus 8, plus 10 minus 6, which is equal to 4. Okay, so then, well, that's the question. Calculate the remainder. So you'd say, therefore, the remainder of is 4. And so that's it.